Thank you. Good afternoon and welcome everyone. Good afternoon in Australia and welcome around the world. It's my pleasure to introduce this webinar from the Global CCS Institute. My name is Gareth Lloyd. I'm Head of Communications at the Institute and I'll be chairing this session. So thank you very much for joining us. It's actually one of a series of webinars that we lead on innovation across the CCS chain, where we bring in leading speakers and give you an opportunity to ask questions and answers. So just in a moment we'll get into the detail of that, but I'm delighted to welcome you to Professor Ozaki of the University of Tokyo, who's going to be making this presentation this afternoon. And just to be clear, we're going to go through the techniques in terms of how this actually works. So the introduction, as far as Professor Ozaki is concerned, you'll see on the slide. He's a naval architect's engineer with over 35 years of engineering and research experience, having completed his doctorate of engineering in 1983. He worked in industrial and R&D centres for Mitsubishi Heavy Industries for 24 years, was appointed a professor at the University of Tokyo in 2008, with research focused on offshore CCS, ultra-deep ocean drilling, ocean renewable energy systems. He teaches in the area of offshore development, engineering and systems, and there's a little piece of advice here for his students, and that is, I encourage you to train well and form good habits while young, something I'm sure we can all take on board. And he's led the current project on shuttle shipping. So I'm delighted to introduce you to him this afternoon. And before we start, just a little bit in terms of housekeeping. What we'll be doing is letting Professor Ozaki give the presentation in just a moment, and we'll be collecting questions from you during the presentation. So if, as he speaks, you have a question, please type into your message box, which you'll see there very clear. And I, as your MC, your chair, will pose these questions at the end, and we should get ample opportunities to ask. What we will do is combine some of the questions where we get almost the same question, and I'm not going to identify who gave the question so we can get the maximum use of our time. So please submit your questions in English directly into the GoToWebinar control panel, which you should see on your screen, and then we will run those straight after the presentation. So at that point, what I'm going to do now is hand over to Professor Ozaki. Professor Ozaki.
Ladies and gentlemen, I'm Masahiko Ozaki, the University of Tokyo, Japan. It is early summer in Japan, one of the best seasons to visit. Azalea is in full bloom in various places, including in and around our campus. Webinar is, of course, very convenient communication tool, but I wish you were here in this fine time. Anyway, I'd like to start my presentation titled Shuttle Ship Transport of CO2. This is the outline of my today's presentation. After checking the key questions, the background of this project will be briefly explained, and the major portion of time will be allocated to presenting the results of our feasibility study on shuttle-type CO2 ship transportation for offshore CCS. The contents are objectives and assumptions, shuttle ship design, cargo tank design, flexible riser pipe, weather considerations, and cost analysis, and finally concluded with summary before the time of Q&A. These are the key questions that I'd like to try to answer in this webinar. Firstly, what are the major benefits of shuttle shipping for Japan? Secondly, is shuttle shipping technically feasible? And thirdly, is shuttle shipping economically feasible? Then I'd like to go to the background conditions on CCS in Japan. As a matter of fact, the energy policy of Japan has not been fixed after the crisis of Fukushima plant in 2011. But from the realistic point of view, measures for reducing CO2 emissions to the atmosphere from the ongoing use of fossil resources are definitely necessary, and the immediate spread of CCS holds the key. As you know, the land shape of Japan is slender, and many CO2 sources, such as thermal power stations, steel works, and so on, are located apart from one another along the coast. And it is difficult to secure a mass storage site. Especially, there is poor opportunity to have geological storage site on land due to the concerns for earthquakes. On the other hand, there are high fishery activities near coast all over the country, and the water becomes very deep outside the coastal zone. So, in order to promote CCS in Japan, we thought ship transport of CO2 from multiple sources to a medium capacity storage site and direct injection of CO2 from the ship through pipe to the sea bottom could be a solution. That is, the mitigating source sink matching, the avoidance of offshore tank storage, and the deep water application using ships are the key points of our conception. This illustration shows a simple sketch of the shuttle ship transport of CO2. Captured CO2 is compressed and liquefied to reduce its volume and temporarily stored in the buffer tanks near port. When a CO2 carrier ship arrives at the port, CO2 is loaded to the ship and transported to the storage site. And then the ship stays within required region with her position-keeping system, while CO2 is injected from the ship directly to the injection well. One of the points in our proposal is the frequent shuttle shipping by small to medium-sized ships. The shuttle shipping allows that the scale of buffer tanks at port is small, and the direct injection of CO2 from the ship to the wells allows that no offshore buffer tanks are necessary. The schematic view in this slide describes an example of shuttle shipping application. In West Europe, for example, since it is possible to secure a mass storage site in the North Sea, the size of the source of CO2 recovery determines the scale and the economical efficiency of a project. Then, the hub concept for enlarging the source of CO2 recovery was thought of, such as Rotterdam Hub project, and consequently, the way of thinking which builds the main artery of transportation to a storage site from the hub has been emerged. The main artery would be realized with offshore pipelines of very large diameter or with CO2 carrier ships of large loading capacity as much as possible. So, the conceptual designs of 50,000 ton ship and even 100,000 ton ship have been proposed. On the other hand, in East Asia, such as Japan, it is difficult to secure a mass storage site, as mentioned before. Therefore, the matching the sources of CO2 recovery and storage sites requires a different approach from the one on West Europe. When a medium capacity storage site is identified, a number of sources will use it, probably despite the distance and the depth of water to some extent. This figure shows another example of shuttle shipping application. That is, multiple sources to multiple sites. In this way, a distributed type transportation system should be developed for East Asia rather than forming a main artery. And we believe shuttle transport by small to medium-sized ships would be appropriate for it. With applying shuttle ships, the route could be flexible. Early startup of project from a small scale and gradual expansion would be possible. If the capacity of one site becomes short, decoupling and moving to another site would be possible. Based on such considerations, technical and economic feasibilities of shuttle-type shipping and offshore operation for CO2 injection from the ship to the well have been examined. This project is carried out under the organization as shown in this chart. Global CCS Institute financially supports the project, and Chiyoda Corporation is the main contractor as the project manager. Under this umbrella, I am the project leader with the assistance of Dr. Osumi, the Central Research Institute of Electric Power Industries, and several companies join for the study of engineering, operation, and regulations. Main components of the proposed system are listed in this slide. In sequence, compression and liquefaction of CO2, temporary storage at port, offloading facilities, shuttle ship with dynamic positioning system and injection equipment on board, flexible riser pipe, whose end is connected with the wellhead on the seafloor, and pickup system at site. The engineering case study is executed under the assumed conditions as shown here. Firstly, nominal injection capacity of one well or a set of wells is 1 million ton per year. So transport system for 1 million ton per year is examined accordingly. Secondly, water depth at storage site is 500 meters. This condition is not so critical technically, but it is influential in riser pipe design. So parametric study is carried out for the riser pipe. And the distance between recovery plant and storage site is varied from 200 kilometers to 800 kilometers. Thirdly, no storage tanks are placed at the storage site. And finally, it is assumed provisionally CO2 is injected at 10 megapascal in pressure and 5 degrees in Celsius in temperature. These conditions are actually specific to the individual project. From now, I would like to show the major results. At first, shuttle ship. We have set transportation system for 1 million ton CO2 per year. That means one day amount of captured CO2 in average is slightly less than 3,000 tons. Considering the operating rate, we set one day amount just 3,000 tons, and then decided the loading capacity of a ship is set equal to the one day amount of captured CO2, 3,000 tons. For distance less than 200 kilometers, 2 ships are necessary in our plan. The time chart described here is an example of operating schedule of 2 ships. One of 2 ships operates at the offshore site on alternate days. Similarly, for distance between 400 and 800 kilometers, 4 ships will be used in turn. This figure shows a general arrangement of a shuttle ship. Length is about 90 meters. Width is 14.6 meters. And draft is 5.6 meters. Not so large ship. Two bilobe type CO2 tanks are mounted in tandem. The service velocity is 15 knots. That is about 28 kilometers per hour. So it takes about 7 hours for 200 kilometers transport. Dynamic positioning system is installed for the offshore operation. In this case study, the cargo conditions of liquid CO2 are set minus 10 degrees in Celsius in temperature and 2.65 megapascal in pressure. In general, ship designers prefer the liquefied gas cargo conditions so that the design pressure becomes low, especially in case that the ship is fairly large and transport distance is long. It's because the volume of one pressure tank can be larger when design pressure is lower, and fewer number of pressure tanks is appropriate to be mounted on the ship. The triple point of CO2 is minus 57 degrees in Celsius in temperature and 0.52 megapascal in pressure. So if the lowest pressure condition is selected, around 0.6 megapascal is enough. But the small to medium-sized ships can hold reasonably high pressure tanks for CO2, and the design temperature can be set at fairly higher. In this way, we have expected that energy cost for CO2 liquefaction can be reduced. And moreover, heat treating process after construction of pressure tank or expensive material use can be avoided if the design temperature is not lower than minus 10 degrees in Celsius. To check the influence of cargo conditions, the additional comparative study has been carried out for the conditions at minus 20 degrees in Celsius and 1.97 megapascal. This figure shows the midship section of the ship. As mentioned before, bilobe type tank is mounted on the ship. Heat insulation is important to restrain the rise of pressure in tank due to the boil of gas. The positioning performance of DPS, dynamic positioning system, have been checked with simulations. In order to make the ship motion minimum, we assumed the ship heading should be kept toward waves. Wind direction is generally related to the wave direction, so two cases of wind direction are applied to check the performance. One is the same direction with waves, and the other is biased at an angle of 45 degrees. Current is usually independent, so the most severe direction, 90 degrees, is applied. As a result, it is confirmed with simulations that the proposed ship can be positioned within 20 meters offset from the target location during operation when subjected to waves of 3 meters significant wave heights, winds of 15 meters per second average speed, and currents of 1 meter per second constant speed. In the next, I'll go to flexible riser pipe. For CO2 direct injection from the ship to the well, a flexible riser and its pickup system are proposed in this study. This figure shows the author's image of the ship during injection of CO2. This slide shows the schematic view of the system for offshore operation. When no ships are there at storage site, a flexible riser pipe whose one end is connected to the wellhead is laid on the seafloor to avoid the severe sea state if occurs. And the other end of pipe is connected with pickup wire, messenger line, pickup float, pickup rope, and pickup buoy in series. When a shuttle ship arrives at the site, the pickup buoy is picked up on board by crews, and then messenger line and pickup wire are wound up. And finally, the end of pipe is connected to the ship equipment to start the injection of CO2. Once more again, I'd like to explain the pickup operation using another slide. The floating synthetic rope between pickup float and pickup buoy is seized with hook bar or something like that by crews. And then messenger line between pickup float and sinker, pickup wire between sinker and the end of flexible riser pipe are wound up one after another. This is one possible measure, and there is room for improvement or introduction of higher technologies. Allowable sea conditions for the pickup operation have been determined by calculations and also interviews with captains of research ships. As a result, 3 meters of the significant wave height shall be limitation for such sized ship, and the offshore operability of Japan's coast is estimated above 90%. This table shows the specification of the designed flexible pipe, and illustration shows the composition of it. The internal diameter of the pipe is about 15 centimeters for the required flow rate of CO2, and the outer diameter is about 30 centimeters as a whole. The buoyant layer is set beneath the outer sheath to mitigate the pipe weight in water for easy and speedy raising of the flexible riser pipe. In order to decide the necessary length of the flexible riser pipe, static and dynamic behavior of the pipe due to the fluctuation of ship position, current, and waves are estimated by numerical calculations. As a result, the tensile strength, the minimum radius of local curvatures, and the fatigue life have been confirmed within allowed range. In addition, we checked the feasibility of the flexible riser pipe use at various water depth sites, and we found that approximately 100 meters and less would be a limitation at shallow side of water if the positioning performance of the ship is same. So, summing up the key technical findings. Firstly, system is technically feasible. Secondly, design considerations allow costs to be minimized. And finally, design considerations ensure offshore operability of Japan's coast at above 90%. In the next, I would like to go to cost analysis. As described here, the cost analysis is done for 30 years of injection, and the assumed life of components is 30 years for onshore plant and offshore facilities, and 15 years for shuttle ships. This is a pre-feasibility study, not for the specific projects, so there are still many other assumptions. Please check the details in the full report if you are interested in. This slide shows the scope of work of the cost analysis in this study. Regarding onshore plant, CO2 tank, CO2 loading pump, loading arm, and related equipment are taken into account. Regarding shipping, CO2 shuttle tanker, including onboard CO2 injection pump, seawater pump, CO2 heater, injection control system, and winches are considered. And regarding offshore facilities, CO2 injection pipe and buoy are considered. A list of items that are out of scope is also shown in the lower half of this slide. That is, CO2 capture facilities, CO2 compression and liquefaction facilities, CO2 gathering pipelines on land, CO2 loading berths at port, CO2 wellhead equipment, pipelines between wellhead equipment and injection well, and CO2 injection well are out of scope for the cost analysis. The results of cost analysis are briefly described with bar graphs. The unit of the numerical values is Japanese yen per ton CO2. The rate of exchange has been full of variety recently, so please allow me not to write down by foreign currency. Capital-related cost and operation cost and management cost are taken into account. And the breakdown is given in a bar graph with color code. From the right-hand side, blue color shows the cost due to CO2 injection. Orange color shows CO2 shuttle shipping. Red shows CO2 tank and loading at port. And light blue colors shows compression and liquefaction, just for reference. The upper bar graph is the result in case that the transport distance is 200 kilometers. And the lower one is the result in case of 400 to 800 kilometers. In the case of 200 kilometers transport, the compression and the liquefaction cost is about 2,400 Japanese yen per ton CO2. And transport cost is about 2,000 Japanese yen per ton CO2. And in case of 400 to 800 kilometers transport, the transport cost rises to about 3,300 yen due to the increase of shipping cost. This slide shows the influence of CO2 curve condition in case of 200 kilometers transport. The upper result is same as the previous one, named base case here. And the curve conditions in temperature and pressure are minus 10 degrees Celsius and 2.65 megapascal, respectively. The lower bar graph is the result for the case that the curve conditions are minus 20 degrees in Celsius and 1.97 megapascal. We expected that upper case would have energy-saving merit in the liquefaction, but the effect is not so significant in this case. Rather than that, the cost for CO2 tanks at port is higher in the base case. It is because the design pressure becomes higher and total cost becomes slightly higher in the base case. But please take care that the additional cost for heat treating process after construction of pressure tank or expensive material use is neglected in this comparative study. Next, this slide shows the influence of seawater temperature at storage site in case of 200 kilometers transport. In order to warm CO2 from minus 10 degrees in Celsius to plus 5 degrees in Celsius before injection to avoid freezing, seawater is used, and some heating system is added if necessary. Seawater temperature in base case is 19 degrees in Celsius and 8 degrees in Celsius in the comparative case. As shown here, there is some cost increase. So summing up the key economic findings. Firstly, system is economically feasible. Secondly, necessary number of ships is stepwisely increased according to distance, and consequently, the cost for transport is as well. And finally, the share of CO2 compression and liquefaction in total cost is comparatively significant. Careful consideration is needed because the utility charges, such as electricity, are dependent on the project and very influential to evaluate it. This slide is the last one of my presentation for summary. First, offshore storage featuring CO2 shuttle ships has major benefits for Japan. Second, the shuttle shipping allows flexible operation linking multiple CO2 sources and multiple offshore storage sites. Third, CO2 shuttle transport by a number of small to medium-sized ships is technically feasible. Fourth, offshore injection using a flexible riser pipe is technically feasible. And CO2 shuttle transport can be cost-effective depending on the distance from sources to storage sites. Thank you for your attention. I would like to hand back to Gareth. Thank you.
Hello, thank you very much, Professor Ozaki, and thank you for the insights throughout that presentation. We're going to move straight on to questions and answers now. And I would just remind you that if you have got questions, we can certainly squeeze them in, so please write them straight into the panel on your screen. And first of all, perhaps a more information question for us as the Institute. Do we get an electronic copy of the presentation? Well, in fact, the presentation slides, the recorded version of the webinar, and indeed the report will all be on the Institute's website shortly, so we'll put the details up at the end of the webinar. And for Professor Ozaki, a question that is coming up out of the presentation that we have here is: do shuttle ships of the similar functionality and size exist today? If not, what do you see as the key challenges?
Okay. In fact, there is no need to use a large-size ship for CO2 transport. There is very few experiences to use a CO2 ship. And coral carbonic, Anthony Leader's belong, is maybe the biggest one, and that's amount of carb is 1,250 cubic meters, I think. So the 1/3 or 1/2 of our proposal.
Okay. And a question which leading on from that is it feasible to design ships which could take LNG, liquefied natural gas, in one direction and liquid CO2 in the other direction?
Okay, the cargo condition is different from LNG carrier and CO2 carrier. Usually, LNG's conditions in pressure is atmospheric pressure, and the temperature is minus 162 or 3 degrees in Celsius. But the cargo tank for CO2 should be pressure tank. So the usage of one tank to LNG and liquefied CO2 is difficult, I think.
Right. And another question, was there any consideration in your work of transporting compressed CO2 instead of liquefied CO2? And how would that have affected the results?
In my conception, CO2 is liquid. Please repeat the question.
Oh, sorry. I'll do that. Was there, in your work, did you consider the transportation of compressed gas CO2 instead of CO2 in its liquefied form? And if you were considering compressed gas CO2, would that have affected the results and created a different answers?
Okay. I have not done the detailed study for the compressed CO2 case. But in general, compressed gas has less density than the liquid CO2. So the
Sure.
Transport efficiency is very lower in the case of compressed gas.
Okay. And consideration of the comparative costs of an offshore pipeline, roughly with your shuttle ship cost calculations. Have you any comments on that, the different costs of the offshore pipeline option compared to shuttle ships?
Okay. In Japan, offshore industries are not so active. So we have very little experiences of construction of marine pipeline. And so we cannot estimate the real costs for pipeline transportation. But we think 100 kilometers or 200 kilometers is the competitive line between a pipeline and ship transportation.
Yeah, yeah. And another one, can you clarify whether LNG ships can actually be used to transport CO2? Is that possible?
It's possible, but I think it is not realistic.
So do you want to explain why that is?
Mm-hmm.
Can you explain that?
As described before, the cargo condition is very different.
So it's technically a completely different proposition. Is that the answer? Yeah.
Yes.
And another question: did the analysis of options for shipping consider using a single larger ship for the 200-kilometer option rather than two smaller ships to achieve a lower total capex cost? So that's the is it better to use two ships for the 200 kilometers option rather than the one, given lower capex costs? This would result in higher short-term injection while the ship is in transit. Have you got any comments on that?
Anyway, our assumption is a relatively short distance transportation. And
Sure.
as you know, the shipping time is a part of the whole time. So we say this is ship, but almost all of the time the ship does is injection of CO2. So from the point of the operability, operational rate, waiting time to for loading of CO2 at port is not effective. So small ship is very effective for the short distance transport and use of many times at offshore.
Okay. Yeah, that's fine. And then here's a practical type question. Can other ships, other vessels become entangled in the floating synthetic rope? If yes, what sort of damage and risks could arise?
There is a risk, but the risk for the other ship is not so high because just a buoy and rope cannot make damage to the ship. But if we lose the buoy, there is a problem for picking up operation.
Okay. And we're getting towards the end of the questions here. What is the economic trade-off of shuttle ship and piping transport to the storage site? So I'll repeat that. What is the economic trade-off? Sorry.
Yeah. So the capital cost is higher in the pipeline, and operational cost is higher for the shipping. So it depends on the situation, I think.
Okay. And does your study mean that storage of CO2 for Japan needs to occur within 800 kilometers of the coastline, given the increasing cost that is experienced as transportation distance increases? So storage within 800 kilometers of the coastline.
No. If the distance becomes longer, the concept should be changed. So in our concept, one ship holds one day one day captured CO2, but the distance becomes longer than maybe 1,000 kilometers. Larger ships should be used for the economy, I think.
Right. Look, I think we've got to the end of our questions at that point, and what I'd like to do at this juncture is to thank very much on your behalf Professor Ozaki for his detailed answers and your presentation. Thank you very much indeed. It is very much appreciated. And as I said at the beginning, all of the report, the presentation, the recorded webinar will be available on our website. You can see the web address there. And I'd also like to add that we are very interested in hearing your feedback. That's the way we can continuously improve these sessions. So if you have some feedback or questions, there may be some question that's suddenly come to mind, please send them in to the address on the screen there, webinar@globalccsinstitute.com, and we'll make sure that they get answered. If it's general feedback on the website, please, on the webinar, please send that through to us. We would like to hear your views. In closing, thank you very much to Professor Ozaki, and thank you to all of those who put in questions and everybody involved. Thank you, and please look out for further webinars from the Institute. Thank you very much.